Hi. So let's continue our tutorials, preparation to exam. So today I will consider the Laplace equation. Consider the first problem. Let D in R2 on x less or equal than 1. This is D. X1, X2. So we are solving the equation Laplacian u equal 0 in D, and let us define on the boundary gamma, let us divide it in two. This is gamma 1 such that x1 more or equal than 0. And this is gamma 2, the second half. Gamma 2, x1 less than 0. So gamma 1 is on the right half of the circle, gamma, and gamma 2 is the left half. And let us denote this point minus 1, 0. This is point A, and the point 0, minus 1, 0, 1, this is point B. So we have 2 points. No, let me write this way. It is A, and this is the point B. Yes? So we have to find the harmonic function inside this circle such that on the right part of the circle from A to B here on gamma 1 it is equal to u on gamma 1 equals to say 1, and u on gamma 2 equal 0. So this is our boundary value problem. So how to find it? Find this solution. No, geometrically it is the following. Let us look at formula. Suppose this is our point x anywhere. Then we know from what we had before in the theory that the angle, this angle, say phi, angle AXB, angle AXB equal phi of x is a harmonic function. Laplacian phi equals 0. So this is a harmonic function. But it has different boundary values. What it is on the boundary. Say, we know from the elementary geometry that this angle phi is constant when our point x is on the circle. Yes? On the gamma 2. But it will be different if it is on gamma 1. So on gamma 2, this angle is, I would say, equals to pi over 2, because this is the right triangle, this angle is pi over 4. This angle is also pi over 4 because this is a right triangle. So phi on gamma 2 equals pi over 2. Now, phi on gamma 1, if on the gamma 1, we have to draw this point x on gamma 1, and our angle phi is this. Yes? So this angle is 2 pi minus pi over 2. So phi on gamma 1 equals 2 pi minus pi over 2 equals 3 pi over 2. So phi is one solution of our equation of harmonic. It is a harmonic function, but it satisfies these a little bit different boundary conditions. It is equal to constant here on gamma 2, constant on gamma 1, two different constants, but the constants are not what we wish. So we have to do something with this function. What can we do? We can multiply this function by some constant. It remains harmonic function. And we can add a constant. Yes, because constant is also a harmonic function. Yes, so consider the function u of x equals, say, c1 phi of x plus c2. So for any constant c1 and c2, this is a harmonic function, and let us find its value on the gamma 1 and gamma 2. So phi u on gamma 1 equals c1 times phi on gamma 1 plus c2 equals c1 times 3 pi over 2 plus c2. U on gamma 2 equals c1 times pi over 2 plus c2. Yes? So we found. And we have to find c1 and c2 such that u on gamma 1 is 1 and u on gamma 2 is 0. So we have the following system equation. C1 times 3 pi over 2. Let me write as usual. 3 pi over 2 times c1 plus c2 equals 1. Pi over 2 c1 plus c2 equals 0. So we have a system of two linear equations. Now let us solve it. If you subtract this equation, then you have 3 pi over 2 minus pi over 2 c1, and the c2 will disappear. This cancels the. So we write 1 and minus 1. Yes, the weight equals 1. Yes. So it is pi c1 equals 1. c1 equals 1 over pi. Now with c2 we have p c2 equals minus pi over 2 c1 from the second equation equals minus 1/2. Yeah, 1 over pi times pi over 2. minus 1/2. And so u of x equals 1 over pi no 1 over pi phi of x minus 1/2. Let us see. So let us check it. On gamma 1, phi of x equals 3 pi over 2, it is 1. So on gamma 2, it is pi over 2 1/2 minus half. Yes, it is correct. Yes, so this is solution. Now what remains is to find this function phi. We have to somehow express it. I think we did it already, but let us do it again. Okay, now it remains to find some analytical expression for the function phi of x. It is x1, it is x2. Here is some point, say x1, x2. X. This is the point A, this is the point B. And we have to find the angle phi. Phi is this angle. Let me draw it in red. Now to find phi, the best is to divide it into two triangles. Let us call this point A, B, C. So we have two right triangles, and consider this angle angle alpha, and this angle beta. Yes. So let us find what can you say about alpha. It is better to find cotangents alpha. Cotangents alpha. So it is the ratio of this side and this side. This is minus x1. And this is equal, so A is 0 minus 1. So it is x2 plus 1, this side. Cotangents beta equals, again, minus x1 times 1 minus x2. Yes, it is this, because B has coordinate 0, 1. Let me write for symmetry 1 plus x2. So, and therefore, well, phi equals alpha plus beta equals cotangents minus 1 of minus x1 divided by 1 plus x2 plus cotangents minus 1 of minus x1 1 minus x2. Yeah. So we found the angle phi, and now we have to substitute it here. But to be sure, let us check this answer. Let us take, say, this point with coordinate minus 1, 0. So phi of minus 1, 0 equals cotangents minus 1 of what? Minus 1, minus 1 is 1 divided by 1, x2 is 0. 1 plus, this also here is 1, and this is also 1. Cotangents minus 1 of 1. So are cotangents of 1. So what is the angle such that its cotangents cotangents is 1? This is of course the angle pi over 4 plus pi over 4 equals pi over 2. So this point. Now let us take, to be sure, this point. Phi of 1, 0 equals cotangents minus 1 of what? Here is minus 1 divided by 1, minus 1. And here is also minus 1 divided by 1. Cotangents minus 1 of minus 1. Now to be sure, let me draw the graph of cotangents. It looks like this. Yeah? This cotangent. So it is 1 at the point pi over 4. Here cotangents is 1. And here is symmetric. So here the point pi over 2 plus pi over 4, this is 3 pi over 4. And here cotangents is minus 1. Yes? And so, cotangents minus 1 of cotangents of minus 1 is 3 pi over 4 equals 3 pi over 4 plus 3 pi over 4 equals 3 pi over 2. Yes, it is the angle, this angle. 3 pi over 2, it is this angle. Yeah. So the check shows that the answer is correct. So our answer is this. We have this ancillary function phi, and then u is this linear combination of phi and 1. That's it. Or you can just write this function, arcotangents times 1 over pi minus 1/2. You can write it as well. Very good. Let's consider another problem. Okay, next problem is the following. Consider the equation Laplacian u equals f equals, yes, f in R3. Yes, so it is a Poisson equation. And f of x equals module x to some power alpha. Yeah. So it is the function which grows, depends only on radius and grows as some power of radius. Solve the equation that find the spherically symmetric solution. Yes? What does mean spherically symmetric solution? It is solution of the form u of x equals u of model x equals u of r. So we are looking for this spherically symmetric solution. Okay. To solve this problem, we, if u depends only on r, then you have to write down the Laplace equation for spherically symmetric function, which looks as follows: u double prime of r plus 2 divided by r. It is in 3 dimensions, so n minus 1 divided by r, u prime of r equals r to the power alpha. So we have to solve this ordinary differential equation. Now let us do it. V of r, it is u prime of r. So you have v prime plus 2 divided by r v equals r to the power alpha. And let us find the integrating factor. No, let me write it. Integrating factor is equals e to the power integral 2 divided by r dr, yes, equals e to the power 2 logarithm r equals r square. So we found integrating factor, multiplied by integrating factor. It is r square v prime plus 2r v equals r alpha plus 2. Now this is complete derivative. It is r square v prime equals r alpha plus 2. R square v equals integral of this, it is 1 alpha plus 3 r alpha plus 3 plus c1, yes. Now divide by r square, it is v equals 1 alpha plus 3 r alpha plus 1 plus c1 r minus 2. Now u is integral of v, u of r integral v of r dr equals 1 alpha plus 3. We integrate r alpha plus 1, alpha plus 2, r alpha plus 2, plus integrate, minus c1 r minus 1 plus c2. So this function is a homogeneous function, yes, of degree alpha plus 2. Now this corresponds to the general fact that if you have a homogeneous function of order say beta, and you differentiate it, take any partial derivative, then the resulting particle result will be homogeneous function of order beta minus 1. If you differentiate it twice, it will be result will have degree beta minus 2. And if you take the sum of this second derivative, it will be also function again of order homogeneity beta minus 2. So if it is other homogeneous function of order alpha, then the initial particle had order alpha plus 2. In fact, this is important thing in itself, so let me explain it more detail. Okay, I wanted to say something about homogeneous functions. So homogeneous functions can be defined as follows. F of x1, xn is homogeneous of order alpha if f of t x1 t xn equals t alpha f of x1 xn. Yeah. So this means that along every ray going from 0, from the origin, the function is just proportional to r, to distance to the origin, to the power alpha, nothing more. Now, for example, we can consider homogeneous polynomials. We had already such beast. Homogeneous, we can now the first rule, so that if f of x, g of x are homogeneous of order say alpha and beta, so f homogeneous of order alpha and g of order beta, then fx times gx is homogeneous of order alpha plus beta. Yes? No, simply because f of tx, g of tx equals t alpha fx times t beta gx equals t alpha plus beta fx gx for any positive t. I have to add that it should be true for any positive t. No, the degree of homogeneity alpha can be both positive, negative, or 0. And the next thing is that if a function is homogeneous of order alpha, then its derivative is homogeneous of order alpha minus 1. But before, I have to give you some general form of homogeneous function. So consider the function f of x1, xn. And suppose that x1, say, different from 0. No, one of them should be different from 0, and let it be x1 different from 0. Then f x1 and so on xn is equal to the following thing. F x1 divided by x1, x2 divided by x1, xn divided by x1. But to have the equality, we have to multiply it by x1 to the power alpha. So if the function f is homogeneous of order alpha, then it has this form. No, to be sure, let it be model x1 to the power alpha if x1 is negative. Yes. So now, if this holds true when so equals 1 moment f of 1, x2, x1, and so on, xn, x1 times model x1 to the power alpha equals model x1 to the power alpha times g. This is constant, it does not depend on x1. So it depends only on x2, x1, xn, x1. Yes? So we have here product. One function is just power of x1, and other function is in fact a function of n minus 1 variable. No, for example, if n equal 2, we have f x1 x2 equals model x1 to the power alpha times g of x2 x1. And now you see here that one function, this function is homogeneous of order alpha. This function is homogeneous of order 0. Yes? So the product is homogeneous of order alpha by what is written here. And now I wanted to differentiate this function and see why this function is homogeneous of order alpha minus 1. No, it is the same for all n, so let me do it for n equal 2. So f of x1, x2 equals g. Okay, x1 to the power alpha. Let me consider, say, case then x1 is positive. If it is negative, it's the same. Times g x2, x1. Yes. So df dx1. Let's differentiate. It is alpha x1 alpha minus 1 times g prime of x2 x1 plus x1 to the power alpha g times g prime x2 x1 times derivative of this with respect to x1 minus x2 divided by x1 squared. And now let us look. This function is x1 to the power alpha minus 1, homogeneous of order alpha minus 1, and this function is homogeneous of order 0. Yes, because it depends on x2, x1. If you multiply both by any t, then the fraction will not change. Here, this function is of homogeneous of order alpha, this of order 0, and this is of order -1. Yes, because here x2 and here x1 squared. Now the f dx2 equals x1 alpha, it does not depend, times g prime x2 x1 times 1 divided by x1. Yeah. Now this is homogeneous of order alpha, this is of order 0, and this is of order -1. That's it. So both functions, here both terms are homogeneous of order alpha -1, and this is of order alpha -1. The same calculations hold in any number of dimensions. No, we can change the role of x1 and x2 if you want to consider domain where x1 is 0. So then x2 is not 0. Yes. So it is all proved. In particular, if f, okay, let me write u of x1 xn is homogeneous of order alpha, then Laplacian u is homogeneous of order alpha -2. Because we differentiated 2 times, every time every derivative of this first order derivative homogeneous of order alpha -1 is differentiate once more alpha -2. With the solution of the Poisson equation, what we did quite right now, there may be some difficulties because, say, not if the function is homogeneous of order, say, -1, and say function 1 over x, homogeneous of order -1, then its primitive function is logarithm x. It is not homogeneous. Yes, so this is the exception, and here we should be, say, more attentive to these details. Okay. Now consider one more problem. It is 4, I think. Consider domain D in R2. It has the following. x1 between minus and plus infinity, so it is the whole line. And x2 between 0 and some L. So it is this strip. Zero, it is L. And we solve the following problem. Laplacian u equal 0 in D, and gamma is the boundary, gamma 1 and gamma 2 is 2 components of the boundary. Gamma 1 x2 equals 0, gamma 2 x2 equals L. So Laplacian u is 0 in D, and u on gamma equals 0. So we want to solve this problem, to find solutions to this problem. Now if our domain were bounded, compact, then the only solution is 0. But here we can see other solutions. Now if you think a little bit, you would find we had the following class of solutions. U of x1, x2 equals, say, cosine or sine of k x1 e to the power k x2. Yes, you remember you can write this solution. This is one of just a few examples which we had, so it is easy to keep it in mind. And here we can have cosine also, and here we have plus and minus. Yeah. No, why it is good with sine? It is not so good here because here sine kx1, so the lines where it is 0 are going vertically. It is x1 equals some constant. So let us change places x1 and x2. So u x1, x2 equals e to the power plus minus k x1 times sine k x2. Yeah. Or cosine, but we are more interested in sine. Then it is a solution of the Laplace equation in the whole plane, but where it is 0. This is not 0, and this is 0, u of x1, x2 equals 0 if the sine is 0, so k x2 equals n pi. Yes? So if this argument is pi, because sine is equal in the multiples of pi, then this means that x2 is pi n pi over k. Now we have to find here pi, k is a free parameter. For any k it is solution. So we have to find k such that for x2 equals L it will be 0 for the first time. This means that here n equals 1, so pi over k equals L. K equals pi over L. Yes? And so our solution is u of x1, x2 equals e to the power plus or minus pi over L x1 times sine pi over L x2. Yes? Then the solution will be 0 for y x2 is 0 and x2 is L. Now it is one solution, the first in series. Next solution will be if you multiply it by n for positive integer n. So a general solution. U of x1, x2 equals, no, let me write C1 E n pi divided by L x1 plus C2 E minus n pi divided by L x1 times sine of n pi divided by L x2. So this is a solution, and of course we can take any linear combination for different n. And having this, we can solve different other problems. Suppose we have the following domain. X1 positive, more or equal 0, x2 between 0 and L. So it is half of this strip. We consider this strip, it is half of this strip. So, you solve problem. Delta U equals 0 in D, U equals 0 on gamma. Gamma is this, it is the boundary of this strip. Now we know this solution. Let us find parameters C1 and C2 so that solution satisfies the additional boundary condition. It satisfies for any C1 and C2 it is 0 on this gamma. Let me write gamma 1, gamma 2 and gamma 3. So it is 0 on gamma 1 and gamma 2 for any C1 and C2, but how to make it 0 on gamma 3? It is easy because on gamma 3 x1 is 0, so this is 1 and this is 1, and so it is sufficient to take C1 equals C2 is minus C1. Say C1 is 1, C2 is minus 1. So U x1 x2 equals C e to the power n p x1 divided by np by x1 minus e minus np divided by L x1 times sinus n pi divided by L x2. Yeah? So this is solution. No, let me write un cn because it depends on n. No, for n equal 1, it will, no, it is the simplest case. And you know that this some difference of exponents can be written in the following form. Un equals Cn hyperbolic sine of p n and p divided by L x1 times sine, trigonometrical sine, n pi L x2. Hyperbolic sine and trigonometrical sine. So this is a solution of this problem. Now, similarly, we can consider solution of the following problem. Let it be the last here. The following problem. We have the following domain. It is rectangle. Rectangle, and here it is L, it is say M, it is x1, x2, so that is gamma 1, gamma 2, gamma 3, gamma 4. And we consider a similar problem, Laplacian u equal 0 in D, u on gamma 1 equals 0, u on gamma 2 equals 0, u on gamma 3 equal sine p L x2, u on gamma 4 equals sine 2 pi divided by L x2. Yeah? It is a little trickier. So here we have just one half wave, and here we have two half waves. And here it is 0. So how can you solve it? No, you can look here. It is more or less half of this problem, because if you take this solution, no, say for n equals 2, so you write u equals v plus w. Yes, first of all, and v and w satisfy the following. V on gamma 3 equals sine pi over L x2, V on gamma 4 equals 0. Yes? W on gamma 3 equals 0. W on gamma 4 equals this, sine 2 pi divided by L x2. Yes? Now let me start from W. W x1, x2. Let me write it, say C1 times the following parabolic sine of 2 L x1, yes, times sine trigonometric 2 pi L x2. It is a solution which was written in this place. It solves the problem in this half strip. It is gamma 3. And this is, and on gamma 3 it is 0. Yes? Because on gamma 3, hyperbolic sine x1 is 0. Now at the point at this it is m at this gamma 4, here this solution will be not 0, and here this solution w of m x2 equal c1 hyperbolic sine 2 pi Lm sine 2 pi over L x2. Yes? So we found solution W here. And and it should satisfy this condition. So this means that C1 times sine should be equal to 1. Yeah? So C1 equals 1 divided by hyperbolic sine of 2 pi over Ln. And so we solved half of the problem. We found W. Now to find V, we just flip this picture. So V of x1, x2 equals C2 hyperbolic sine of pi divided by L, this time pi divided by L without 2. Instead of x1, I write m minus x1. Yes? So it starts from here. Times sine of pi over L x2. Yeah. So this function, no, of course, it is harmonic because harmonic function does not change if you say change the sign of one of the coordinates. Because second derivative does not change if you change x to minus x. And now if x1 equals m, this is 0. Yes, and now we have to have that this product for v 0 x2 equal C2 hyperbolic sine of pi over L m, x is 0, time sine of pi over L x2. And this should be 1. And so from here C2 equals 1 divided by hyperbolic sine of pi over Lm. So this way we found V with this constant. We found V here with this constant we have pi and W, and their sum will satisfy these conditions. So we frequently use this strategy when you solve equations with say some boundary conditions. We represent our solution as sum of two or more terms. Each term satisfies part of the conditions and the other should be 0. Yes? And then their sum will satisfy all set of conditions. No, okay, let us finish for now. Yes, have a good time. Bye.